Hello Gators, this is 8.7 volumes with cross sections, squares, rectangles, triangles, and semicircles. Let's take a look at a volume of a prism. A loaf of bread is a rectangular prism. How about let's look at one slice of bread, which is also a rectangular prism, a nice thin one, and find the volume of the slice of bread, add up all the volumes, and that'll be the volume of the entire loaf. Think of the one slice of bread as the area of the base times the thickness. The thickness in this case could be delta x. And so what we would do is we would take all of these little thicknesses of all of these loaves slices and add them up, and that would be the volume of the loaf of bread. Let's use this in this problem. We have an area here caught between two curves, and we are going to find that the cross section is a square base, and the thickness, since it's perpendicular to the x-axis, the thickness is delta x. This length is a side, and this length is also a side, the same length because it is a square. The formula for the volume will be area of the base times the thickness. The base is a square, s squared times delta x. In order to figure out the length of this side, we're going to do y of the upper minus y of the lower. We're going to square it because that'll give us the side squared. And then we're going to replace the y's with x's, where the volume will be the sum of all of these little slices. And then we will make it into an integral from 0 to 1, and then we'll write out the integrand. So this is the way we do it, just like slices of bread. That's what we're doing. Let's take a look at a Geogebra demo. This is the same curves that we were working with, and you can see this is the lengths right here. This is going to be the side of the square. If I go ahead and turn this, you can actually see the squares in a 3D formation here. And if I increase the number of slices here, you can get a better feel for the volume that's being created by these squares here. And let me go ahead and put this back. I'm going to be referring to it again. Let's take a look at this next problem. It's the same area, but this time I want to make the squares perpendicular to the y-axis. Perpendicular to the y-axis would mean this s would be right here, and this would be the other side of the square. And the thickness is no longer delta x because it's perpendicular to the y-axis, so the thickness will be delta y. So when we look at this, it'll be the area of the base times the thickness. We've decided the thickness is delta y. Instead of working with y's, we're going to be working with the x of the right minus the x on the left. And to get these x's, I'm going to take both functions and solve for x. This will allow me to now put the x on the right here and the x on the left over here. Now I can estimate the volume by summing up all of these little thicknesses, all these little kind of slices. And then to find the actual volume, it'll be the definite integral from 0 to 1. Why is it still 0 to 1? Because this point is 0, 0, and this point is 1, 1. I'm now referring to the y-coordinates, and the y-coordinates are the same as the x's in the last problem. So delta square root of y minus y squared, quantity squared, dy. And this is how I set up the volume. Let's take a look at another problem. This is another shaded area. What we're doing now is we are going to take a look at a rectangle perpendicular to the x-axis. So again, the rectangle's here. It looks like the height is twice the width. So if this is the width, this length right here is the width, then the height will be twice that, and the thickness will be delta x since it's perpendicular to the x-axis. So the area of the base is no longer a square, it's length times width, and this width right here is actually a y-coordinate because it goes from the x-axis up to the curve, so it's a y-coordinate. Then the height right here is 2y, and this ends up being 2y squared, And since y is x cubed, I'm going to substitute that, do a little simplifying, and my volume will be the integral, and it looks like my x's go from 0 to 2, and then I'm going to have 2x to the 6th power dx. And then I can either use my calculator or find it using the fundamental theorem. Let's take a look at this problem. We have the same area that we're working with, but the cross sections are now perpendicular to the y-axis, and they are still a rectangle, but this time the height is always the number 6. So here again is perpendicular to the y-axis. That means this thickness will be delta y. This is going to be a some kind of width, and our height will always be the number 6. So we know this height will be 6, and the width will be the x on the right, and the x on the right is the number 2, minus, and now we want the x on the left. I need to solve for x here. So x equals a cube root of y. So this will be cube root of y. And then the thickness we decided is delta y. So now this will be 6 parentheses 2 minus cube root of y delta y. And that would be a representation of this kind of slice, like a bread slice. And then the summation will be all of these slices. And the volume will be the integral. And this point right here, we're going from right here, this point is 0, 0. And this point will be 2, comma. And if I put 2 up here, that'll be the number 8. So I'm looking at y's now, so I'm looking at this y and this y. So it'll be 0 to 8, 6, 2 minus cube root of y dy. And this will be the setup for the volume of this. All right, let's take a look at volumes of cross sections using triangles and semicircles. We're with the same picture again. Same area, but this time our cross sections will not be a rectangle or a square. Instead, they will be an equilateral triangle. And this is the way it's kind of look, like these little equilateral triangles. And it's sitting perpendicular to the x-axis. So let's go ahead and create a little piece of volume. So this is going to be the area of the base times the thickness. And the thickness is going to be delta x. And the area of an equilateral triangle is s squared root 3 all over 4, where this stands for s. This is our s, the side of the equilateral triangle. In this case, this side will be the y of the upper minus the y of the lower, quantity squared times root 3 over 4 delta x. And remember, the y of the upper is root x minus x squared root 3 over 4 delta x. Okay, let's go to our definite integral, and our little x's are going to go from 0 to 1. And if you want to write root 3 over 4 first, that might not be a bad idea. Minus x squared, quantity squared, dx. So this is the representation for the volume that's created by that. Let's take a minute to go to the Geogebra and see what that looks like. I'm going to deselect square and select equilateral triangle. And I'm going to go ahead and show you what the 3D drawing looks like. See, these are triangles now, no longer squares. And if I increase the number, you can get a better sense of the volume. And let's make that, and we're going to revisit this one more time. So let me put it back where it was. Now let me go back to our program here. And now we're going to take a look at a semicircle. Oh no, we're doing isosceles right triangle. So now we're going to have a triangle, but it's not going to be equilateral. It's going to be an isosceles right triangle where one of the legs is going across. So let's go ahead. Our delta V will be the area of the base times the thickness. And we're perpendicular to the x-axis, so that'll be a delta x. So this little thickness is delta x. This is one of our legs, so I'm going to call that a side, and this is also going to be a side, and this is actually half a square, so it'll be actually 1/2 s squared. And so we are going to again do our y of the upper minus y of the lower, so that's square root of x minus x squared, quantity squared delta x. And our volume will be equal to the integral. We're going to go from 0 to 1, and we'll have 1/2 root x minus x squared dx. And that represents the volume that is formed by these cross sections. Now let's talk about a semicircle. So the semicircle, the diameter is going all the way across, and then we have this rounded piece right here. So delta V will be equal to area of the base times the thickness. We always start off the same way. The base will be 1/2 pi r squared, and the thickness will be delta x. And so then we'll have 1/2 pi, and our radius is going to be, actually this is a whole diameter. So this is a diameter, and I really only want half of that. So I want half of that diameter and delta x. Okay, now if I square that, that's going to be 1/4. So at the end it'll be 1/8 pi, and then I want my diameter, and my diameter will be this upper minus lower, so this will be root x minus x squared, and then delta x. So I need a half of that diameter to be the radius. And then I can set up my volume. It'll be the integral from 0 to 1, and I'll have 1/8 pi, and then this will be root x minus x squared, quantity squared, delta x, and that'll represent the volume created by that. All right, and our last one, cross-section demonstration. Here we go. Now I'm going to deselect equilateral, go to semicircles, and you can see the semicircles here. Let's go back, and here's our last one. The region bounded shown to represent the solid. Find the volume of each solid based on the given cross section. So we have this area being formed by these boundaries, and we want equilateral triangle cross sections perpendicular to the y-axis. So perpendicular means it's going to be delta y. I am going to be working with the x on the right, and the x on the left is always 0. So I'm really just working with the x coordinate right here. And to work with the x coordinate, I'm going to solve for x, and when I solve for x, that'll be y cubed. So this will be the x on the right. That's determining the x on the right. So our little delta volume will be equal to the area of the base times the thickness, and this will be s squared root 3 over 4 times delta y. And if we want to write the root 3 over 4 in the front, our s will be the x of the curve squared delta y. And I want to replace that x I have replaced it with y cubed. And now I can kind of clean things up. The volume will be the sum of root 3 over 4 y to the 6th power delta y. And our volume will be the integral, and this will go from the y0 up to y equal to 2 root 3 over 4 y to the 6th dy.